Hello, welcome to the video tutorial series of Multiscale.Sim. In this video, multiscale analysis of laminated composite will be demonstrated. This tutorial can be found in tutorial document of the linear version, workbench, tutorial. I will demonstrate the Chapter 3 multiscale analysis of the laminated composite today. Before demonstration, let me give you the brief overview of the analysis. So we will perform the multi-scale analysis of the laminated composite material consisting of the cross-weave material and unidirectional reinforcement. As you can see here, this is our target laminated composite microstructure model. Boundary condition can be seen here as a phase at one end and the pressure is applied on the surface. So this is the overview of the macro model and boundary condition. And our laminated composite is composed of the 4 layers. The first and the last one is a GFRP cross-woven composite, and the second and the third layer is the GFRP unidirect composite. So as shown here, we will consider the two fiber orientation pattern for the unidirect composite, 0 degree and 90 degree. So for the analysis, as a procedure, the step 1 will be the homogenization analysis. In the other word, numerical material test for GFRP unidirected composite. We will perform the numerical material test and then obtain a material constant. And then for the second step, we will perform the homogenization analysis. In the other word, numerical material test for GFRP cross-woven composite. Also, we will obtain the material constant from this model. Then after that, as a step 3, we will perform the microscopic structural analysis of laminated composite by using the material constant obtained from the step 1 and the step 2. Then, finally, the last step, we will perform the localization analysis. This localization analysis is performed to see the stress state of the microstructure of our laminated composite. And then as a very important note, you need a license for the linear and nonlinear version of the Multiscale.Sim, as well as a Mechanical Enterprise or Mechanical Premium or Mechanical Pro to perform this tutorial. Multiscale.Sim can be opened by Multiscale.Sim Launcher application. You can find Multiscale.Sim Launcher as can be seen here. Right-click, select Run as Administrator. Click Yes. Select the version, select the license, and select the environment you would like to use. Here I will select Workbench, then click Run. Now, Multiscale.Sim can be seen here, and it can be successfully opened in the NC Workbench environment. To perform unidirect composite homogenization analysis, from the analysis system, double-click on the static structure, or you can just drag it down on the project schematic. Since we will perform the homogenization analysis, we will name it like homogenization analysis, like this. Then click on the engineering data to define the material properties of fiber and matrix. Click on the engineering data source. Find Multiscale here. As you can see, there is a glass fiber and select the epoxy resin elastic. Then close the engineering data. Now we will create unidirect composite by using SpaceClaim. Geometry templates are provided on SpaceClaim and also in the design modeler, but in this tutorial, I will use the SpaceClaim to create the model. So to create the unitary model by SpaceClaim, click on the geometry, right-click, click on the Multiscale.Sim geometry, and here you can find the provided geometry templates of the Multiscale.Sim. So select unitary. Then double-click on this unitary. After waiting for a few seconds, SpaceClaim is open. Here is the input parameter. Click on the unitary and the script. Right-click, select Edit Script. You can find the script information here. So our model input is fiber fraction is the 50%, filament fraction percent is the 100, and fiber length is set as 0.1 milli. To create the model, click on the unitary, left click, and click on Run Script. As you can see here, the script is running and model is created successfully. You can check the fiber diameter information here. Close the SpaceClaim. To perform homogenization analysis of unitary model, double-click on the model. After waiting for a few seconds, SC Mechanical is launched. You can see the geometry here. Here is the matrix highlighted in the green, and the other 5 fiber bar are shown in the green color. So we will assign the material properties of the matrix and the fiber. To assign this, click on the matrix, and from the material assignment, select the epoxy resin elastic. For fiber, select all the fiber part. From assignment, choose glass fiber. Then material property is successfully assigned. After that, we have to check the unit system. Here, it is the millimeter, kilogram, Newton second, so the metric system is okay to use. Then we will create a mesh of the model. To create a mesh, click on the mesh and select the mesh here. Select the sizing. To select the body, click on the body here. Select all the body by Control-click, except for the mid-fiber. Then click on the Apply. Then define the element size. Here we will define 3.3 10 power minus 2. Then select sizing again. Select the remaining part. Click Apply. At 7.5 10 power minus 2. Then click on the mesh. Right-click, Generate Mesh. Here our analysis model is successfully created. Then to perform the homogenization analysis, click on the static structure. Select the Multiscale.Sim. This is the linear analysis, so click on the linear, then select the homogenization analysis. You can see the homogenization setting appear under the static structure. Here we have to define the material name and material description for the material constant calculated. So give the name GFRP 50%, description as unitary volume fraction 50%. Okay. And then select the home. You can click on the solve, or you can also select on the static structure, right click, and then solve. Now the simulation is running and homogenization analysis is in progress. Now simulation is finished within a few seconds. And then you can click on the MSK homogenization from the solution tab. Here you can see the material name, GFRV 50%, material description, UD volume fraction 50%. Here is the EM modulus. As you can see, X, Y, and Z direction. Of course, the X direction is the largest. Y and Z, it's the same because they are symmetric. Shear modulus, Poisson ratio, and density. Then we will check the stress evaluation based on the numerical material test data of our micro model. So to see this, select the solution first, and then select the Multiscale.Sim again. To check the elemental result, select the stress. As you can see here, under the definition, the testing type can be seen uniaxial tension of X direction. So we will check all 6 directions. In that case, do the same operation for 6 times. One, two, three, four, five, six. The first one is for X direction, so the second one, choose Y direction. That one, Z direction. Fourth one, XY. The fifth one, YZ. And the last one, XZ. Okay. And then click on the solution, right click, evaluate all result. Now, in a few seconds, the operation is finished. And click on the each direction. This is the X direction, numerical material test, stress distribution. This one is a Y. This one for Z. Here's the shear XY, shear YZ, and shear AZ. So if you want to check the animation, you can click on the play. And then stop. Let's check the XY direction. Play. You can also adjust the animation time here. Okay. So now the homogenization analysis of the unitary composite is finished. From now, we will move to step 2, homogenization analysis of GFRP cross-woven composite. As you can see here, the fiber part of the cross-woven composite is composed of the unitary composite material. So in that case, we will use the material constant obtained from the step 1 in step 2. To perform the homogenization analysis of the cross-woven, same as before, we will create a new analysis system. So select the static structure, drag it on the project schematic. Let's define the name, homogenization analysis cross-woven. Okay, then we will open the engineering data. Click on the engineering data source. Select the multi-scale. As you can see here, we will select first the epoxy resin. And then here, this is the material constant obtained from step 1, GFRP 50%, and also the description as we provided here. So we will select this and close the engineering data, and then recheck it. Here the engineering data are already assigned. From now, we will create the cross-woven composite model. To create the cross-woven composite model, this time design modeler will be used. So click on the geometry, right-click, and select the new design modeler geometry. After waiting for a few seconds, design modeler is launched. Then we will set the unit as a micrometer in this case. The advantage of design modeler is that you can specify the unit system you would like to use, meter, centimeter, millimeter to micrometer scale. Okay, to create cross-woven model, click on Hide Content Cross-Weave. Okay, as you can see in Details view, you can input the model parameter. So, and then click on the Generate. Okay, now the model is already created. As you can see, the matrix part is here, and there will be the full fiber part. And close the design modeler. Double-click on the model. Okay, as the mechanical is launched, you can check in geometry, matrix, and full fiber part. So first we will assign material. Click on the matrix, assign epoxy resin. Select all fiber. Select GFRP 50%. For cross-weave model, we need to define fiber orientation. To define fiber orientation, click on the geometry, and here you can see element orientation. Element orientation will be used only for fiber, so let's hide body for matrix. Then we will define fiber orientation for the first fiber. So also hide body for the other fiber. Click on the element orientation, select body, apply, and then you need to define the surface guide. So for the scoping method for the surface guide, select the surface that is perpendicular to Z-axis. So this surface. Select all surface by Control-click. Then click Apply. Then we need to define edge guide. Edge guide is to define X-axis. X-axis means fiber orientation direction. So select one edge here and then click on the extent, click on the limit, and you can see the whole edge line selected. Then click apply. Okay, so do this operation for other fiber as well. And element orientation, select geometry. So fiber orientation certified for all fibers. We will click on the element orientation and generate orientation. Okay. To check all four fibers is not easy to clearly see, so see the one fiber and check it. So the red color is the fiber orientation direction. So the red direction is so the red color defines the x-axis, which is the fiber orientation direction. So you can see that the fibers are oriented in this direction. And I'll show you another fiber body. So in this fiber also, fiber are oriented in this direction, the red color direction. So there is no problem with the fiber orientation. So after defining element orientation, we perform the linear homogenization analysis. So click on the Multiscale.Sim, click on the linear homogenization setting. As before, we'll define the material name as GFRP. This time is a cross. 35%. Okay. And then click on Home, click on Solve. Okay, now homogenization analysis is finished, and you can check the data by click on the MSK homogenization. Here's the material name we define, and you can see modulus value X and Y are the same because they are symmetric. You can check the shear modulus, Poisson ratio, density, and also elastic matrix data. We will move to step 3, which is macroscopic structural analysis. So as explained before, our laminated composite has two types of the material constant. The first layer and the last layer is the cross. The second and third is the unidirect. So we will apply the step 1 material constant to second and third layer, and the step 2 material constant to first layer and then fourth layer. To perform microstructural analysis, as before, create new analysis system. Set name as macro analysis. Double-click on engineering data. Click on engineering data source. Since I already selected Multiscale, you can see the material constant calculated in step 1 and step 2 here. Add this engineering data to analysis system, close the engineering data, and then double-click on it again to recheck it. Now the engineering data are already assigned. We can confirm that. Close the engineering data again. Laminated composite geometry is provided in tutorial example 5. In that case, right-click on the geometry, select Import Geometry, and then click on the Browse. And then please go to your destination folder. That means the installation folder of Multiscale.Sim. For me, I have installed it on the C program file, Multiscale, and then this version is the 242, so I select 242, select the example folder, and in sample geometry, you can find the plate laminate solid.stp file. Select this file, click Open. Okay, now geometry is successfully imported. Then double-click on Model. Okay, and SIM Mechanical is launched. So in geometry, we will assign material properties. Select the first layer and last layer. Select GFRP cross 35% material. Then select the second and third layer. Assign GFRP 50%. Then let's define boundary condition. Click on Static Structure, and you can see the Environment tab here. We will define the fixed boundary condition at one end, so click on the Fix. Fixed boundary condition will be defined at the X0, Y0, and Z0 surface, so here, this full surface. To select the surface, click on the Face. Select the surface by Control-click, then click Apply. Okay. Then we will apply the pressure on the top surface. So from Environment tab, select Pressure. We will select the top surface. So click on the surface, click Apply. Set 0.1 megapascal as pressure value. Okay. Then we will double check the unit system. Here is the unit. And we will select Celsius here. Then click on the solution. Right-click, Solve. Okay. Now simulation is successful. To check the contour of the stress and the deformation, click on the Solution tab. And then from the Solution tab, you can select the deformation, strain, or stress that you would like to check. So select deformation. We will check the Z direction deformation because we apply the pressure in the Z direction. So click on the directional. Here in definition, directional deformation, orientation will be selected as DAZ. Okay. And then for stress, we will select normal stress. And for the coordinate system, we will select element type. Then click on the solution, right-click, and select Evaluate All Result. Now you can check the directional deformation, normal stress, and element type. So the last one here is to check the X, Y, and Z axis of the element, because we need to define the correct fiber orientation for our analysis, and you can check it by using this option. For directional deformation, maximum deformation of minus 14.5 can be seen at the edge. This is the normal stress. And for element try, change it to the wireframe mode. Okay, and then from display view, select front. You can see that the element coordinate system is same as global coordinate system. For the next step, we will consider the 90-degree unidirect for the second and third layer. In that case, we will change the coordinate system of second and third layer. We will remove the wireframe view. To create the coordinate system for the layer 2 and the layer 3, click on the coordinate system, right-click, insert coordinate system, or you can also click on the coordinate system and coordinate system as shown here. So first, the origin is defined by the geometry selection, but we will define the origin as global coordinate. What we would like to hear is that to define element coordinate, X direction is in same direction of global y-axis. So in that case, here is the principal axis. Axis is X, and we will define by not global x-axis. We will define global y-axis. Okay. Then modify the layer 2 and the layer 3 coordinate system from default coordinate system to new coordinate system that we define. So after changing the coordinate system, let's try to solve the analysis again. Right-click on the Solution tab and click on Solve. Okay. So first, I would like you to check the coordinate system that we defined first. So click on the element try. Change it to wireframe to clearly see the coordinate system. Height body for layer 1 and layer 4. So only layer 2 and layer 3 can be seen. Then click on the element try again. Select Display, View, Front View. So now you can see that global y-axis direction is same as x-axis of layer 2 and layer 3 element. It means fiber in this element are oriented in one direction. So let's confirm first layer and fourth layer again. To do this, height body of layer 2 and layer 3, show body for layer 1 and 4. Then click on element types again. Here you can see first layer and fourth layer is defined by the global axis in the same direction of the y and in the same direction in x and in the same direction in z. So let's check how our deformation and normal stress are changed. with respect to fiber orientation. Let's do shows all body, remove wireframe, view, and then click on directional deformation. Now as you can see, there are minus 19 milli, about minus 19 milli deformation at the edge here, which is larger than the previous case. The orientation of material principal acid affect the result. Now is the last step to perform localization analysis. Localization analysis is performed to know the stress state of the microstructure of the macrostructure. To do that, click on the Multiscale.Sim. Here, Localization. Click on Extraction. So now there is a localization information and a solution tab. You can select any element in this macrostructure. So to see the mesh, click on the element here. Click on the geometry here. Let's choose one element in the middle. Click Apply. So this is element number 683, as you can see here. And then click on this localization information, right click, and click on Generate. Okay, data extraction is successfully finished. And you can see the strain data and reference temperature data appear here. Then close this macrostructural analysis. Since I have selected the first layer, let me show you again. For localization, I have selected the first layer here, which is the cross-woven composite. So in this case, we need to import the localization data to cross-woven. Therefore, create new static structural analysis system by dragging it onto model of homogenization analysis cross-woven. Then open the parent model. Okay, so static structure B5 here is homogenization analysis or cross-woven, and static structure 2 D5 here is for localization analysis. Therefore, click on static structure 2 D5. First, we will check the unit system, temperature as Celsius, and metric system is applied. Then click on Multiscale.Sim, click Localization, and click Localization Setting. So localization settings appear in static structure 2 D5. In details, you can see the strain data as we imported here, and then temperature data. Click on the solution, right-click, and solve. Localization is successfully finished. You can see the green check mark here. So to check the stress of the microstructure, Click on the solution, click on stress, and select equivalent for meshes. Right-click on the equivalent stress, click Evaluate all results. From Geometry, Height, Matrix Body. Okay, then click on Equivalent Stress again. As you can see here, it can be confirmed that stress is concentrated in these two fibers, in which the fiber direction is in X direction, and fiber direction, which are oriented in Y direction, do not contribute to stiffness. So Chapter 3 tutorial is finished here. Thank you for watching our tutorial series.